Hopefully you recall a few special values, one being the mass of the Earth equal to approximately 6 times 10 to the 24th kilograms. You might also remember that the mass of the Moon is about, let's call the mass of the Moon lowercase m and the Earth capital M. The mass of the Moon is about 7.35 times 10 to the 22nd kilograms. And the distance between the two of them, we'll call it r subscript em, is equal to 60 times the radius of the Earth. Now that translates to a value of about, let's see, calculate that. The radius of the Earth is 6.4 times 10 to the 6th meters. So if we multiply that times 60, we get about 3.84 times 10 to the 8th meters. Okay, well, here's the question at hand. If you were to park some spacecraft, the space shuttle, if that were exactly halfway between the Earth and the Moon, then the force of gravity between, we'll call the mass of our spacecraft m prime, there'd be a couple of forces to calculate. There's the pull of gravity between the Earth and the spacecraft. This would be capital G times m prime times capital M, the mass of the Earth, divided by r over 2 quantity squared. There'd be a smaller amount of force pulling to the right because the Moon isn't as massive. This force would be capital G times m prime times lowercase m, the mass of the Moon, divided also by r over 2 quantity squared. So the question is, where would we have to move the spacecraft, so that the force vectors are equal and opposite? Well, if we move it closer to the Earth, that's only going to tip the scales even more in favor of the force of gravity from the Earth dominating. So the spacecraft would have to be moved somewhere over here. So let's take a look at this. Undo some of my work. Okay, let's redo this one. And just say that the distance away from the Moon is some value that we can call, how about x? What is that value in order for the net force of gravity to be equal to 0? Well, here we can apply the superposition principle and just say we'll calculate each force individually and then add them up and see that they're equal to 0. So if Fe, the force of gravity on the spacecraft from the Earth, plus F sub m, the force on the spacecraft from the Moon, is equal to 0, that means that the magnitudes of these forces, the force from the Earth and the force from the Moon, have to be equal in magnitude but opposite in direction. So G times m prime times the mass of the Earth divided by, well, let's see, if we label this distance as x, then the only thing we can call this distance would be, r minus x, right? Okay, so g m prime times m over r minus x quantity squared has to equal g m prime lowercase m over x squared. Now we can cancel out a lot of values here. G appears on both sides of the equation. And it turns out we don't have to ask the question, what if we put the space shuttle right here? What if we put a basketball right here? What if we put you just floating in space right there? A house. Doesn't matter what the object is, its mass is going to cancel out of the equation anyway. So what we're really finding is the point in between the Earth and the Moon where the net gravitational field is equal to 0. So now we have from step 1 to step 2 to step 3 an expression that says the mass of the Earth divided by r minus x quantity squared has to equal the mass of the Moon divided by x squared. Or in other words, r minus x over x quantity squared has to equal the mass of the Earth divided by the mass of the Moon. So you might be tempted to expand this expression by squaring it, but maybe an easier approach would be just to take the square root of both sides of the equation. So we get r minus x over x is equal to the ratio of the mass of the Earth divided by the mass of the Moon. And this gives us mr minus mx equals capital Mx. So let's get all the x's together on one side of the equation. We have the quantity capital M plus lowercase m quantity times x would be equal to lowercase m times r. So x is equal to little m over r divided by big M plus little m. So in this case, x is equal to 7.35 times 10 to the 22nd times 8.34 times 10 to the 8th. 3.84 times 10 to the 8th. 3.84 times 10 to the 8th divided by 6 times 10 to the 24th plus 7.35 times 10 to the 22nd. Grab your calculators and see what you get. This comes out to 0.012 times 3.84 times 10 to the 8th, which is equal to 4.65 times 10 to the 7th. So this distance is relatively small. I don't think I've drawn it correctly. I think the distance is even farther over here, much closer to the Moon than it is the Earth. But that makes sense because the mass of the Earth is so much greater than the mass of the Moon. So there's one example where we can apply this principle of superposition. Here's another one. What if you were standing at some point and you look to the north and you see a Ford F-150 parked at a distance of 20 meters away, and we'll say the mass of a F-150 is about 1,800 kilograms. You look directly to the east, and an Audi R8 is parked 15 meters away, and the Audi has a mass of about 1,500 kilograms. Then what's the net gravitational force acting on you? So again, we'll apply the superposition principle. You're attracted to the Ford F-150, and you're also attracted to the Audi R8. I don't know which one you're more attracted to, but we can find out by applying Newton's laws. So there's one force vector acting on you that pulls directly to the north, and that would be a value of g times your mass times the mass of the Ford divided by 20 squared. And then there's another force, the attraction between you and the Audi, and that force would be g times your mass times the mass of the Audi divided by 15 squared. So let's say your mass is 70 kilograms. So this is 6.67 times 10 to the negative 11th times 70 times 1,800 divided by 20 squared. And the other force is 6.67 times 10 to the negative 11th multiplied by 70 times 1500 divided by 15 squared. So again, grab your calculators and see what you get. So I get 2.1 times 10 to the negative 8th newtons as the force of attraction between you and the Ford. And I get a force of 3.1 times 10 to the negative 8th newtons as the force of attraction between you and the Audi. Now, why is the Audi is less massive? It doesn't seem like you should be as attracted to a less massive object. But then again, you're standing closer. And the ratio in the distances squared is more than enough to overcome the smaller amount of mass. So let's draw this as a force diagram. There's one force pulling up, and it's not quite as strong as the other force pulling to the right. This is a force of 2.1 times 10 to the negative 8th newtons. This is a force of 3.1 times 10 to the negative 8th newtons. So we can find the net force by using the parallelogram method of vector addition. Make lines parallel to each of the two forces, and the net force can be represented by this vector that really seems to be nothing more than the hypotenuse of a right triangle, so we can use the Pythagorean theorem to say the net force is equal to the square root of 2.1 squared plus 3.1 squared, and then we can multiply all that times 10 to the negative 8th newtons. Last step on your calculator then. Okay, and hopefully you get the same final answer as me. The net force you would experience would be 3.74 times 10 to the negative 8th newtons. You might be interested in what's the angle that you're being pulled at. You're being pulled more upward or more to the right. Well, you're pulled more to the right, so this angle for the net force is going to be something less than 45 degrees. If you want to find out exactly how much, we could say tangent theta is equal to the force along the y-axis divided by the force along the x-axis. So this would be 2.1 times 10 to the negative 8th newtons divided by 3.1 times 10 to the negative 8th newtons. But of course the 10 to the negative 8th newtons cancels out, so we can just take the inverse tangent of 2.1 divided by 3.1 and find that the angle is about 34 degrees.